Good afternoon, everyone. Today we're going to start discussing time series analysis. Okay, so the file that I shared with you has some codes on it about time series analysis. I'm sharing with you some references here. These are good references. So this one is from Penn State University. It's a good resource on time series analysis. There's also this resource on writing mathematical equation for ARIMA. And then also this one, excellent resource from Duke University. Okay, so let's open some of these sites. Okay, I already opened this, share this with the other class. Okay, so let's take a look at that. Okay, this is from Penn State University. Okay, Penn State. So they have this, it's from one of their subjects, Stat 510, and this is applied time series analysis. We'll take a look at some of the concepts, the theories behind time series analysis. All right. So what we're going to focus on is a univariate time series analysis. Okay, so as the name suggests, univariate means it's a sequence of measurements of the same variable collected over time. Okay, so you're only dealing with one specific variable. If you're looking at several variables at the same regular time intervals, then you have what we call a multivariate time series. For this part of our discussion, we're going to focus on univariate time series analysis. Okay, so what's the objective of a time series analysis? And to distinguish it first what's the difference between a cross-sectional data and a time series data? A cross-sectional data, as we said, takes a look, it's a snapshot of your data at one point in time. For example, 2022, you're looking at several individuals. For example, you're looking at the GDP of several individuals, several units, like all countries. Okay, so you have different units, different countries, and you're taking a look at their GDP in 2022, for example. So that's what we call a cross-sectional data series, cross-sectional data. On the other hand, a time series takes a look at one unit, just one individual, one unit, at different points in time. So if you take a look at the Philippines and its GDP from 1970 to 2022, then that constitutes a data where you have the GDP measured across different time periods from 1970 until 2022. And that's only for one individual, one unit, which is the Philippines. That's what we call a time series. When you combine these two, cross-sectional and a time series, then you have what do you call that, class? The combination of the cross-sectional data and a time series is? Hello? What do you call that, class? Hello? Can you hear me? Hello, class? What's the name for that? The first one is cross-sectional, the second one is time series. What's the combination of cross-sectional and time series? You have several units, data of which are taken from different points in time. Kunyari, ASEAN, no? ASEAN countries. You're taking a look at GDP. So you have several units. You take a look at their GDP from 2000 up to 2022. So that's a combination of cross-sectional because you're taking a look at different countries, and then time series because you're also considering the time component. So taken across several time periods, that makes it a time series. Taking a look at it from different individuals, that's a cross-sectional data. And yes, you're correct. It's called a panel data. All right. We call it a panel data, cross-sectional and time series combined. All right. Now this one, our discussion for this one will be just time series, so one individual, one unit taken across several points in time. Now I'm going to post my video lecture on panel data. And as Fin students, it's important for us to know how to navigate or how to analyze panel data. So we might not have the time anymore to discuss in class panel data, but I will assume that you'll watch the video on panel data. Okay, not because it's a requirement, but it's because you have to know. Okay, you have to know. In fact, I'm almost tempted just to jump to panel data, but I said that might be difficult to grasp immediately if we go to the panel data without even going to the time series. Because cross-sectional, we have already done so many cross-sectional data via OLS. So this will be the first time that we're going to do time series. All right. So what's the basic, what can we do with the time series analysis? Of course, aside from describing the time series pattern, taking a look at it, if there's a trend, if there's seasonality, if there's long run cycle, we can also forecast the values. Okay, we can forecast the values and predict what will be the values in the next few periods. Okay, the model that we're going to use, as mentioned before, is the one developed by Box and Jenkins. Okay, it's called the ARIMA model, autoregressive integrated moving average. Okay, so before we even go to the modeling of the data, of the time series data, we need to look at the data itself. Is there a trend? Is there seasonality? Are there outliers? Does the data exhibit long run cycle? Is there constant variance? Are there any abrupt changes, the level of the series of the variance? These are important questions that we need to address just by looking at the data. Okay, so this is an example of a time series data. Okay, so this is from, you have 99 observations, 99 consecutive years. So this is a time series plot of the annual number of earthquakes in the world with seismic magnitude over 7. Okay, in the 1950s, you can see here that there were so many earthquakes with magnitude 7 and above. So dito, sorry, I'm sorry, it didn't state the year, no? For 99 consecutive years, we don't know where this started. We don't know where this started. But you can see here that in this period, there were many earthquakes with magnitude 7. And here, fewer. And you can see here that this time series does not have any trend. So if you're going to take a look at this, the series, looking at these parameters, these pointers, there's no trend. You cannot see an upward or downward trend. As far as outliers is concerned, we don't, does not seem to have outliers. There are no data sets that really stand out by being very, very high or being very, very low in terms of the numbers. Okay, what else? Long run cycle, that will be quite difficult to determine. We have to dig deeper in order to answer this. And how about the variance? Okay, is there a constant variance? Hard to tell, but there seems to be a constant variance, but it's hard to tell just by the plot. You have to do some statistical tests in order to determine if the variance is constant. Okay. Also for abrupt changes, maybe here, this can be considered as an abrupt change. From this year, there were around 35 earthquakes approximately 35 earthquakes with magnitude 7 or more. And then the following year, there were less than 10. So these are abrupt changes, drastic changes in our data. Okay. All right. So here, no constant trend, no seasonality in the data, no obvious outliers. It's difficult to judge whether variance is constant or not. Okay. So one of the simplest model that we can use is what we call an AR1 process. So what's an AR1 process? Autoregressive. So we said that this comes from the Box and Jenkins approach in modeling time series, ARIMA, autoregressive integrated moving average, and we're going to explain what that model is, ARIMA model. So this is an AR1 process. Autoregressive means that you're modeling your time series based on its past values. Auto means self. So you're not using any exogenous variable, you're using the variable itself. If you're modeling, for example, the sales of a particular company, if you want to predict and create a time series model, then you're going to use the past values of the sales of the company. And if you're doing that, you're creating what we call an autoregressive model. And an autoregressive model of order 1 means that you're using the past values of your data. Okay, so for example, if this is your time series, 13, 14, 8, 10, 16, okay, then you're going to get the order 1 means, so this is your earliest data, okay, 13 is your earliest data, sorry, 13 is your latest data, so this is your x sub t, this is your x sub t minus 1. Okay, so what we're going to do is, we're going to get the log 1 value, okay, t minus 1, okay, so, wait, t minus 1, that means this is quite t1, t2, okay, so this is the most current value, but log 1, parang mali ito x of t minus 1 is the log 1 value of x sub t. All right, so the log 1 value should be 14. Okay, so that means you're going to get the past value. You're going to get the past. I don't like how it's presented here. Okay, we'll just create another time series. But what log 1 means is that you're going to use the log 1, the log value, the prior value. Okay, so you're going to use this data, this time series of previous values in order to predict our original time series. Okay, we're going to work on that. We're going to have an example. All right. So this is the plot of your log 1. Okay. And the equation of an AR1 process looks like this. So our original data, x sub t, we're going to model that. So in order to predict our x sub t, we have this intercept delta plus phi1, which is the coefficient of x sub t minus 1. Okay, plus wt. So you notice that your model is based on the previous value of your series itself. X sub t minus 1 means order 1 or of order 1 siya. Okay, past value. And your error terms here is identically and independently distributed and normally distributed with mean 0 and constant variance. Okay, so this is the assumption that your residuals should have 0 mean and then constant variance. If it does not display this, then it will violate the assumptions of a regression model. So we will have to test for we'll have to diagnose a time series. Okay. So this is essentially the ordinary simple linear regression equation, but there's one difference. Although it's not usually true, the ordinary least squares regression, we assume that the x variable is not random, but instead is something we can control. That's not the case here. Okay, that's not the case here in this problem. All right. So if we regress this, if we run the regression, you'll find here that the log one, the x sub t minus 1 at 0.54 is significant. P-value is less than 0.001. Okay, so log 1, that x sub t minus 1 is a significant predictor of your x sub t, which means that we can use the past value of order 1 to predict our time series x sub t. Okay, so we look at another example here. We can find here that this series has a trend. Okay, it has a trend. However, the variance seems to be constant, but we're not so certain about that. If you can see this one, there's a trend here, right? You know, trend, yeah, it's going up, and the variance okay, seems to be constant across the index. But again, we're not sure about that. There is a way to test whether there's constant variance. Okay. All right. So I'll leave you, class, to... So dito, what did it do? Apparently, may seasonality siya, no? Diba? You see the pattern, there seems to be seasonality. No? Ayan, no? It exhibits both trend and seasonality. If we use ordinary regression methods, so ito yung regression natin, di ba? X sub t is, this is beta 1 times t. Alpha 1 times, this is for season, the first seasonality, the second seasonality, the third seasonality, the fourth seasonality. This is for the trend plus epsilon sub t. Okay. Sometimes we may add quadratic for the time, because we can surmise that this can also be, sorry for my pen seems to display some quadratic trend, no? Not necessarily just a linear trend. Kasi parang nag-i-increase siya over the index. Right? Exponentially. Okay. So I leave you to look at the other concepts here. All right. This one, we're going to look at this. ACF, this is the autocorrelation function. And this is the PACF. There's no PACF here. The partial autocorrelation function. Autocorrelation, this is also autocorrelation. But walang PACF. Okay. So, this is a full lesson class, no? Ito yung mga ano niya. Lesson 1. Okay? And R code to, no? It uses R. So you can use this, copy the code, and then run it. Okay? You can run it and follow along. Okay, but we're not going to use this data. We're going to use another data. Okay, there are other references that I shared with you. This one is an excellent resource, the one but by Duke University. But I'll leave you guys to look at that. Okay. All right. We're going to use these packages. Forecast, FPP3. Quant mode is a package that is of great importance to us. And then if you have difficulty loading TSM, kindly chat. Okay, so kindly install these packages. You may use Pacman and then load it using library. I'll give you a few minutes to do that. Okay, you may do that now. Let me pause recording. Please remind me that my recording is paused. So if you have difficulty loading TSM, that means it hasn't been archived in CRAN yet. So we can do this. Kindly install the remotes package, and then we will load the TSM package directly from the GitHub of Kevin Kodzi, the one who developed this package. So you can install that package as remotes, and then let's use remotes, the namespace. It's where install that GitHub comes from, and then it will get that package from Kevin Kodzi's GitHub. Okay, so kindly just run this. Okay, let me also run these packages. All right, when you're done, please kindly chat. Should be able to load. Okay, thank you, Margaret. Because we're going to use TSM in getting the autocorrelation function and partial autocorrelation function. Okay, good. Thank you. All right, so let's give your classmates a few more seconds. All right. So I hope everybody has loaded the TSM package in their computers. Okay, great. Thank you. Thank you for your feedback. Now, going back to our discussion on time series analysis, as I mentioned a while ago, time series analysis deals with extracting meaningful insights from our time series data. Okay, so that we can use it to and creating a model so that it can be used to forecast future events. The method that we're going to use is a very popular and very powerful Box-Jenkins approach. So this was developed in the 1970s, and that's up to now it's still fairly popular with modelers or with the statisticians, with engineers, the ones who need to model time series. And Box-Jenkins approach, Box and Jenkins developed what we call the ARIMA process, which means autoregressive integrated moving average. So the AR component there means that we're using the past values of the series itself. The MA takes into consideration the past error terms to model the time series. And the integrated there means you do some manipulation first with the data before you can use the Box-Jenkins approach. Okay, our data has to be what we call stationary. So this is very important about stationary data series. Stationary. Okay, maybe we should, okay, it's best to, let me see if the site that I provided you with, can we check this one by Duke? If this shows us a control V, stationary time series. Okay, all right, not much. Okay, not here. Okay, so let's just Google it. Stationary time series. Okay. Then let's, so quickly, stationary time series is one whose properties do not depend on time at which the series is observed. So maybe let's take a look at images. Okay. All right. So if you take a look at this, let's use this. Okay, this is a good diagram. Let's visit this. Achieving stationarity with time. All right. So this one, you have this plot. This is a stationary series. So what sets a stationary series apart from a non-stationary series? When you say stationary series, there are two components there. Number one, it has a constant mean. Okay, when you say constant mean, it means that there's no trend. If you take a look at this, across time, the mean of this data, of this time series, does not change. Okay, unlike this one, this is non-stationary with respect to mean, MEAN, the average. Why? Because okay, let me annotate this. If I just look at this portion of the time series, the mean is here, right? Average, around that. But if I take a look at this portion of the time series, the mean is around here, the average. So you notice that the average, the mean of the time series changes with respect to time. Unlike this one, okay, regardless of the time, the average remains the same. So this is constant, sorry for so difficult to write here, constant mean. The mean is constant. Okay, so this is non-constant mean. So what are the characteristics for it to be considered stationary? Number one, the mean should be constant. Okay, and the second one, the variance should be constant. So if we take a look at this time series, for example, you notice that our data fluctuates. So we have some high points here, some low points here. But its fluctuation is fixed. Okay, it does not move out. Unlike if you have, for example, if you have this, if you have a time series that's like this, what do you notice? Okay, the variance of the data is increasing across time. All right, so this is what we call non-constant variance. Okay, this is constant variance. This one, the variance is not changing over time. It's the same. So this is what we call a stationary series. Why is this a stationary series? Constant in mean, constant in variance. Okay? This is non-stationary. It's not constant in mean. It has a trend. However, it's constant in variance. All right? So the variance is constant, but the mean is not. Here, it's also non-stationary. The mean seems to be constant, but the variance is not. Seems to be increasing over time, like this. No? May fanning out siya. Okay? And how about this one? How about this one? So this is, on the other hand, time-dependent. This is time-dependent variance. This is time-dependent covariance, which means that the data points are, they covary. They covary with each other. So this is why we call it a non-stationary series. So if your time series data is non-stationary, then we cannot use the Box-Jenkins approach to model that data. We have to do some transformation or modification with the data and then convert it into a stationary time series. All right, so Rick, just remember, class, that you cannot use Box-Jenkins approach or the ARIMA model if your data is non-stationary. We will have to transform the data into a stationary time series. Okay, so just by way of example, An AR1 process, as I mentioned a while ago, an AR1 process is, sorry, I didn't put this in LaTeX. All right, y sub t, this is our time series, is equal to a certain intercept, a certain constant, plus this is the coefficient of your log 1, okay? This is autoregressive 1. Why is this autoregressive 1? We are regressing or modeling your y sub t based on past values of y sub t. And order 1, which means that we are regressing y sub t on its 1 lag, lag, past value, plus a certain error term. So this is your autoregressive 1 process. If it's 2, AR2, then you have 2 past values, y sub t minus 1 and y sub t minus 2. Multiply that by the coefficient, okay? You'll oftentimes see that this is phi sub 1 in many other references. They make use of a sub o, phi sub 1, phi sub 1 times yt minus 1, and then plus phi sub 2, and then y sub t minus 2, and then plus your error term. All right, so this is an AR2 process. An ARP process, of course, will mean that you are regressing your y sub t on p lag. So this is y sub p. Okay, how about an MA process? On the other hand, an MA process, moving average process of log 1, is a model of your time series where you're using past error terms. So this is epsilon t minus 1, okay, times b1, and then plus the epsilon at time t, epsilon sub t. So if it's an MA2 model, then this should be y sub t is equal to a sub t plus b1, and oftentimes b1 here is written as theta 1. Theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2, and then plus you have your epsilon sub t. And you have here your constant, okay? No, not constant, is a sub t, and this is equal to your y sub t. And you can get this, okay, so this is your MA2, and then your MAQ will be Q lags. Okay, so we can also combine yung AR1 process, MA1 process, the combination of which is your ARMA 11. So ARMA 11 siya. So what's the equation for an ARMA 11 process? Y sub t is equal to your intercept a null plus a sub 1 times y sub t minus 1. So this takes care of your AR1 process. And then this takes care of your MA1 process, epsilon sub t minus 1. All right? And then we have this one, difference, PDQ. Ano yung PDQ? Let's say ARIMA 1, 1, 1. Okay, so what does this mean? ARIMA 1, 1, 1. ARIMA PDQ. The P stands for the coefficient for the AR process. The Q stands for the coefficient for your MA process. The D there is differencing. So what's the meaning of differencing there? When you say differencing, you're now generating a new time series. So you're subtracting y sub t with y sub t minus 1. And the value that you're going to get is now your new time series. It's your difference time series. Okay, Now, why do we have to do differencing? What do you think? What's the purpose why we need to do differencing? Anyone? Bakit nagkaroon ng D dito? If you see a model ARIMA 111, okay, the first one there is your P. This refers to your lag of your AR process, autoregression process. The next one here, Q, this refers to the lag of your MA process. No? And this one, D. Ano yung D? D stands for difference. It means you're going to transform your data. Okay, if that's 2, PDQ for example, 1, 2, 1, ang ibig sabihin nun, yung model natin, order of 1 AR, order or lag of 1 for MA, and then you have 2 differencing. Okay? So ano yung differencing nun? What is it used for? Why do we difference our data series? Any venture, Gus?
Sir, may I
Yes.
guess po?
Yeah, sure. Go ahead, please.
I think, sir, it's to make the time series into stationary.
Okay. All right. Thank you, Angel. You're correct. No? You're correct. So if you have a time series just like the one we showed you a while ago, okay, thank you. Angel is correct. So if you have a time series like this, ito, we said that you cannot use Box Jenkins here. You cannot use ARIMA here. This has to be converted into this type of data, a stationary time series. If it's not stationary, then no can do. Okay, hindi pa siya pwede, kailangan natin i-convert into a stationary time series. All right? Now, how can this be converted into a stationary time series? So there are processes, okay? Thank you, Krisha, you're correct. To transform the data, yes. Si Arnel din sinabi, si Emil, to make the data more stationary, okay? So, of course, you don't say more stationary. It's either to make the data stationary, okay? Because there's no such thing as less stationary or more stationary. It's either the data is stationary or not. So if we have a data like this, you cannot work using Box Jenkins. You cannot model this. So what should we do? We have to convert it, transform your data into a stationary time series. So, okay, what are the general rules? If your data has a trend, pag may trend yung data, ibig sabihin, it may be, okay, if your data looks like this, no? It's going up like this. Okay, the variance may be constant, okay? So it may be constant in variance. However, it's not constant in mean. Okay, the average is changing over time. Dito, at this point, the average is this one. Diba? At this point, dito sa point na to, ang average niya, around this one na. At this point, the average is already about here or higher. So you can see that the mean, the average, is not constant. So a data series like this is non-stationary. Therefore, how do you quote unquote cure the non-stationary quality of the data? If it's non-stationary, then you can do what we call differencing. Okay, yung difference, you get the difference between the value at y sub t and then y sub t minus 1. In Excel, that's very easy, no? May function, there's a function for differencing. Okay, so you're now going to create a new data series na, di ba? Hindi na yung original na data series. Bago na, we can call it difference data. And usually, if the data has trend, but the variance is constant, then you only need to difference. So when you difference the data, then what will happen is that it most probably will become stationary. So if the data is now stationary, you can model that. Now, take note that what you're going to model now is the difference time series, okay? Not the original time series. Because remember, if the original time series is not stationary, then we cannot proceed with the ARIMA process. But we can transform the data, make it difference data, and when it's difference already, usually the trend is removed. So if the trend is removed, and assuming that the variance is constant, then what happens is that your data has been transformed into a stationary data. And if it's transformed into a stationary data, then you can now apply the ARMA, ARMA, whatever fits the data. All right. So you difference the data to make the data stationary. Okay, note I didn't say they're more stationary. No? It's either it's stationary or not. Okay, how about if there's constant variance? If the variance is not constant? If the variance is not constant, if there's a fanning out, for example, of your data, if your data is distributed like this, no? So yung variance niya is not constant, it's increasing across time. If that's your, okay, kunyari ganito, no? Yung time series natin gumaganyan. So definitely the variance is not constant. No? So this is not stationary. Now, getting the difference will not treat this. It cannot be treated just by getting the difference. So the way to go about this is to get the log transformation. Get the log of that. Get the logarithm of your data. So once you get the logarithm of the data, chances are your data will become constant in variance. So if it's already constant in variance, then we're okay. You can now model the data. But the data that you're going to model is not the original data. It's not y sub t. Okay? It's not y sub t, but what you're going to model now is log y sub t. Why? Why is it that we're going to model this and not y sub t? Because y sub t is not stationary. What is stationary is log y sub t. So this is the one that we're going to model. But the question is, I'm interested to predict not the log of the y sub t, but the y sub t. No problem. After we have modeled it using log y sub t, then we can convert and compute for the y sub t. Okay, we'll just exponentiate this. And whatever value you get, you can convert it into y sub t. However, class, we need to make it log first in order to make it stationary. Otherwise, there's no point in discussing prediction. Okay? Because we cannot predict. We cannot predict if this is not transformed into a log. All right, now what if there's trend, non-constant mean and non-constant variance? What do we do? What do we do, class? Any suggestion? Non-constant mean, non-constant variance. On both counts. So you have a data like this. No? But it has a trend and the variance is not constant. And may finding out siya, no? All right, so if you have data like that, definitely it's not stationary. Non-constant mean, non-constant variance, aka not stationary. Okay, what do we do with that, class? How do we now transform this so that we will now have a stationary data series? Any suggestions? Any suggestions, class? Okay, the way to go about this is to, get the log and get the difference. Okay, so which should come first? Getting the log and getting the difference, or getting the difference and then getting the log? What do you think? And why? Class, anyone? Volunteer? Volunteer, class? We have a data that displays a trend. We have a data where the variance is not constant. So on both counts, you have non-stationary data. Okay, how do we address that before we can make use of ARIMA? Hello, class. Hello. Any suggestion? Okay, let's see. I saw a chat here. Emil, kindly share your answer to everyone, please.
Sir, I said that
Okay.
we should do the difference first in
Okay.
order to remove the trend and
All
then
right.
apply log to make
Okay.
both of the data stationary.
To make both of the data, you're only dealing with one data, huh, Emil.
Ah,
To make the data stationary. Okay.
yes, sir.
Okay. So thank you. Thank you. Let's see. If you get the difference, okay, let's come up with a hypothetical data. So let's say I have 10 here. This is the latest, and then 9, and then uh, again another 9, and then an 11, and then a 10, and then a 12. Okay. So we will come up now with a new model, a new data series. Let's call it dy sub t. Okay, let's call it, this is our y. Let me call it dy. So what will our dy look like? So it's difference, right? So 10 minus 9, that's 1. And then 9 minus 9, that will be 0. And then 9 minus 11, that will be negative 2. 11 minus 10 will be 1. 10 minus 12 will be negative 2. Okay, so that's now the difference data. Okay, and then Emil suggested that we also log it. So first difference and then take the log. So let's call it L dy, the log of the difference of y. Okay, what's the log of 1, class? What's the log of 1? Kindly check, please. O, dito sa R, no? Paki ano, log of 1. Paki-type log of 1. Yung log sa R, automatic, ang ano yan, default niyan, ang base niyan is E, no? All right, log of 1 is 0. How about log of 0? What's the log of 0? Okay, not defined. What's the log of negative 2? What's the log of negative 2, class? Hello, class. Log negative 2. I'm getting the logs of all of this. Okay, not a number, okay? All right, so order is important. What we do first is to get the log, okay? Why can't we take the difference first? Because getting the difference will generate negative numbers and even 0. And we cannot get the log of these numbers, okay? Unless you do another transformation. Because you can actually do this, no? What you have to do is to find the most negative. For example, the most negative is negative 5. If the most negative is negative 5, what you do here is to add. Okay, you add, let's say 5.01. You add 5.01, what happens now? If you add 5.01, you make all these numbers positive. Okay? If the smallest number is negative 5 plus 5.01, you get 0.01, right? And the rest also will become positive because negative 5 is the smallest number. Okay, but we don't want to do that. We don't want to, again, adjust this. So just first get the log, and then after getting the log, get the difference. All right, so you will now have instead of log difference, you'll have a difference log y. Okay, this is perfectly okay. We will not encounter problems with this one because we of course we assume that the data is all positive. No? If you're dealing with, let's say, sales, you're dealing with stock prices. Okay, if you're dealing with those data, it's not possible to have a negative there. If you have a negative value there, it means something's wrong. How can you have a negative, for example, negative sales, okay, or negative inventory? If you're dealing with inventory, Okay, so first get the log and then get the difference. So you have the difference ng log ng y. Okay, we can name it any way you want. So difference log of y. All right, so that's what we do in order to address your non-stationary data. All right, log transform data and then difference the log transform. So here I specifically started with log and then difference. Okay, once we have generated this new data, of course, you have to plot it, okay, and check if it's already stationary. There are different tests, okay, to check stationary data. You have the augmented Dickey-Fuller test and the KPSS test. Okay, the name is quite difficult to pronounce. No? All right, so these are two examples of tests, and we're going to do that to see if our data is already stationary. Because once we have this, then the next step, once our data is statistically shown to be stationary, then the next step is to plot your ACF, which is your autocorrelation function, and your PACF, your partial autocorrelation function. Okay, what is this used for? This is used for identifying whether we're going to use an AR process or an AMA process, or both, an ARMA. Okay? Now, when we did differencing with our data, we will now be using ARIMA PDQ. D here stands for differencing. But if it's only log, then it's still ARIMA PQ. Okay? However, take note that the data now will be different. If we did the difference and then the log, we're now modeling a different data series, right? Because we have already transformed the data. And then later on, after we have modeled our data, we can go back. We can go back and convert to our original data. Suppose these are sales, and if you want to generate sales, generate the forecasted sales for the next 10, let's say 10 days or 2 weeks, etc. Okay. Of course, we do not use the difference log sales. That will not mean anything to the marketers, to the other people in the department. You will have to convert. Okay, after we forecast the data for, let's say, 10 days, next 10 days, or next 15 days, okay, you'll have values of the forecast of the D log difference log Y sub T. Okay, you'll have to convert that back into Y sub T. We'll have an example of that. Okay, all right. So step 6 is all about helping us determine what type of model is this. Will this be an AR process or an MA process? Okay, but that was before, no? Today, class, since we have so many packages in R that can immediately tell us already, so no-brainer na nga ngayon. Kasi kami dati, before when we were doing this, we have to plot the ACF and the PACF. Okay, because from the PACF, you'll be able to determine if it's an AR. Okay, let's take a look at example. Okay, let's see. Okay. Let's see, ACF. ACF and PACF plots. Take a look at this. ACF and PACF plots. All right. Okay. For example, this one. Okay, so you have ACF and PACF. Okay, now we're going to use this. Take a look at this one, for example. We're going to use this. Take a look at this. We have a PACF here. No? Okay, this is order 1. This is order 2. Okay, you have this blue band here. Okay, you have this blue band here. If your bars are outside the horizontal line, then that means they're significant. They're significant. We call it spikes. Huh? Okay, so what's the partial autocorrelation used for? It is used to determine if you have the presence of an AR process. So since we have a significant spike here at log 1 and also at log 2 and also at log 3, this could indicate that this is an AR, maybe AR2 or AR3 process, or maybe AR1. We even have significant spikes here towards the more later, farther logs, no? Okay. So the PACF is used to determine if the model that we're going to use is an AR process. Now the ACF, on the other hand, will give us a hint if the model that we have to use is an MA process. Okay, so you use the PACF, partial autocorrelation, for purposes of determining if this is an AR process. On the other hand, this one for an MA process. So in this case, since both have significant spikes, perhaps we can test if this is an ARMA process. Combination, AR process, MA process. All right? Is that clear, class? Could I have your confirmation if clear explanation dito? Okay, thank you. All right, so you use the ACF and the PACF in order to test, okay, if the series is an AR process or an MA process. But of course, it's not foolproof. So that's why when I was studying this decades ago, we would do this manually, no? Kasi wala pa namang mga packages ni Arnon. So matagal na proseso to. No? And then, ano pa, yung trial and error. You do trial and error here. Kasi, let's say, if I imagine I will have to test. Kasi syempre, you start with a more simple model. So baka AR1 process lang to. And then you check, baka MA1 process lang. Or baka ARMA 11. Right? Okay, yung spikes dito, my question dito si Angel, thank you for that question. The spikes here in the ACF and the PACF will tell us if the model, the time series model, should be an AR process or an MA process. We use the PACF to determine if it's an AR process. We use the ACF to determine if it's an MA process. Okay? All right. Did that answer your question, Angel? All right, thank you. Now, okay, let's take a look. See, ACF and PACF plots for white noise. There's such a thing as white noise. Okay, tingnan natin to. And take a look at this. Ito. All right. So this one, okay, you can see this one. So yung blue bands natin, itong dotted line dito, no? All right, now it's 0 to so 0, log 0, definitely the time series will be correlated with itself, no? Log 0 to ibig sabihin you're correlating the time series of y sub t to y sub t. Siyempre 1 yan. Okay, kaya don't be confused with this one. Bakit siya significant? 1 nga. Hindi. That's log 0. If you take a look at the different logs, wala There are no significant spikes, no? Tapos dito din, sa PACF, wala ring significant spikes. Okay, what's this? This indicates that hindi na natin mamomodel yung time series natin. Yung PACF, wala nang significant spike dito. Yung ACF, wala na ring significant spike dito. So what does that mean? Okay, it means that the model is okay. The residuals now are, so this was the plot of the residuals, no? So ibig sabihin, nag-model na tayo, tapos chinek natin yung residuals. Remember, pag nag-model tayo, meron tayong exact value, yung actual value ng time series natin, and then meron din tayong predicted value, di ba? So you'll get the difference between that, the predicted value, and the actual value, you'll have your residuals. And then when you create the ACF and the PACF of your residuals, ibig sabihin nito, wala na tayong mapipiga sa residuals natin. Okay na yung model natin. Okay, this is what we call white noise. Yan. White noise na yan, no? Okay, it's called white noise, which means yung residuals natin, we cannot draw out any more out of that. When your residuals are like this, kung ang residuals natin ganito, no? Again, yung kanina tinignan natin, na may mga ito, no? Hindi, white noise yata to eh. Okay. White noise din to, no? Yung kanina, di ba, may mga significant spikes at lag 1, lag 2, lag 3. When your residuals are like that, for example, ito, PACF na to, no? Alright, tingnan nyo, may mga significant spikes. O, di ano to? It means, kung PACF to, meron pa tayong model dito na ARIMA, no? AR process, kasi PACF to eh. Okay, it means that we haven't, this is not yet white noise. So, ibig sabihin na may pwede pa tayong ma-model dyan. Alright, so the goal is that after we model, dapat yung residuals natin white noise na dapat, no? Yung pinakita ko. So this is very important, yung ACF and PACF. It's not only used to determine kung AR process ba siya o MA process, it's also used to determine kung white noise na ba yung ano natin, yung model natin, yung residuals natin. Alright? So and then you identify the best ARIMA model based on that, no? Okay. And then, once again, test, plot the ACF and the PSF for the residuals, ito yung sinasabi ko kanina, to ensure no more information is left for extraction. All right. Now, it's almost time, class. Okay, so let me just show this. No? At least, we start with this data. Kasi kanina, umabot na kami dito kanina, no? sa the other section. So let me also post the discussion this morning para at least pareho tayo. Kasi it's almost time, pero hindi pa natin na-discuss. No? So let's just quickly get this. This is from the datasets package, yung data air passengers. So very quickly, i-load lang natin yung air passengers. So andyan na siya. Okay? And then i-view natin. So this is look, it's a vector, it's a time series. No? It's a time series of data. May I have a 2-minute extension class, please? Just to discuss with you what this time series is all about. Okay, but if you need to go, no problem. I'll just discuss this quickly and then post this sa ano natin, canvas natin. All right. So if you take a look here, we named our 8 air passengers as AP for easy reference. So AP ang tawag natin sa kanya. And then let's take a look at the head of AP. So ito yung mga ano niya, no? So yung data natin time series siya. January to December 1949, okay? Hanggang until let's see. Let's take a look at the structure of our AP. So this is a time series, 144 observations from 1949 to, this should be 1960, no? Kasi 12 years. From 1949 to 1960. Kasi from 1949, that's up to 1960, that's 12 years. All right. So I leave you, class, to look at this. That this is just telling us, you know this, kung mayroon bang missing values. Yung frequency niya is, ibig sabihin, monthly to. Yung cycle niya, ito yung cycle niya. No? So ito yung years, 49 to 60. And then ito yung month 1, okay? So ang cycle niya 12, no? 12, every 12 months. Right? Okay. So let's plot this. Let's see. Pinat natin siya and take a look at our data. All right. Stationary o hindi? Quick answer, please. Is this stationary or not?
No, sir.
Definitely not, no? Merong trend. Constant invariance? Looks like not. Mukhang hindi siya constant invariance. Hindi rin siya constant in mean. Okay? Yung variance niya, lumalaki over time, ano? So you don't have constant variance, you don't have constant mean. So this is a candidate for transforming your data. So most probably, kukunin natin yung ano nito, log, tapos kukunin yung difference. So if you want to model that, ganun ang gagawin dito, no? Kailangan log, a difference log to. Okay, but first, one at a time muna. Tingnan muna natin log. Definitely maglo-log tayo dito kasi mukhang hindi ano. If you try getting the difference, no? Okay. Next time na, no? Kasi may time na talaga. So this is another plot. All right. Let's take a look at the box plot. This is just the box plot. We can see here the plots per month, no? This is January. Ito yung lahat ng mga January, no? From 1949 to 1960. Yung July, mukhang mataas yung ano, no? May mga high points dito. Okay? And you notice that the median is highest in July. Okay? So, we can decompose this. We can decompose our data set. And it will show us here yung decomposition niya. Yan. Ito yung data natin. Ito yung data natin. Then in-extract, may seasonality siya. So apparently mukhang sa July, mataas yung ano, July and I don't know which month, no? August, July, mukhang mataas yung air travel. So this is your trend. May trend siya. This is your seasonality. Okay? This is our data. This is the noise. After extracting yung seasonality and the trend, ito yung natitira. Pero mukhang may pattern pa rin sa trend, no? As a remainder. All right? So, just this last one, ito matetest natin class kung yung AP natin, this one, using the T-series package, we can test using the augmented Dickey-Fuller test. Run lang natin to quickly. Okay, and then this will tell us, okay, hypothesis niya, the series is not stationary. Okay, what's our p-value? 0.7807. So we fail to reject the null hypothesis that the series is not stationary. Not stationary nga siya, no? Ang alternative hypothesis niya, stationary. So here we were able to prove that our series is not stationary. So kung not stationary yan, hindi natin pwedeng magamit kagad hindi natin pwedeng magamit ARIMA, but let me just, I'll end in this. Okay, ito, kino-compute ko na, pinapakita ko yung autocorrelation function at saka yung partial autocorrelation function. Number 1, PACF, is significant at log 1. Okay, ito yung 0, no? Ito yung 0. So dito, this is 1. Okay, may significant spike siya at log 1. May significant spike at log 2 din. Okay, meron nga din dito sa log 1, 2, 3, 4, siguro 12 to, no? Okay, may mga significant spike siya, ibig sabihin, malamang pwedeng AR yung model natin. Ito naman, ACF. Okay. Slow decay. Ang tawag dito, slow decay. Alright? So kapag ganyan, class, pag slow decay, okay, this may or may not mean that may MA process. Pero definitely ito, class, we can say that we have here an AR process, no? Okay, pero class, remember, AP pa lang to, hindi pa natin transform to. So we have to transform the data first before we can do the model itself. All right? So let me end in that. Thank you so much for your patience. Let me stop recording.